start anytime, right?
Yeah.
Okay.
Please.
Okay. Good afternoon, ladies and gentlemen. Thank you for joining today's class. So again, today's schedule it's about HPLC. So maybe you have heard of the word HPLC many times. So this is a conventional HPLC system, which we have in our laboratory. So it looks a bit messy because of the connection tubes. And this big bottle is the bottle of the waste, actually. So the small bottle is the eluent. So usually we use the bottle itself to recycle and to use it like this, so that we can save some bottles. So, well, this system is very old, right? At the moment, we don't use it right now, but it is in the central lab. So some of the organic synthesis lab will use it for preparative. So if you just look at these photos, it is difficult to see the components. So I will use easy understanding. This is the details component of liquid chromatography. So for many weeks, we have talked about the color materials, the mechanism, absorptions, ion exchange, affinity, size exclusions. So as you can see from these slides, HPLC system consists of 5 important parts. Of course, we need a pump to pump the eluent, the mobile phase, which is a liquid for HPLC. And then before reaching the column, we have an injector. So the injector will determine how much sample we can inject into the column will depends on the size of the column. Yeah? So the standard injector size is about 10 microliter for a conventional column like this, with 4.6 mm diameter, with the length 30 centimeter. So, and column oven, if you look at these photos, this big one is the column oven. So usually the column is placed vertical, like this, vertical. So, and then the column usually is not, sometimes for some separations, you need to increase the temperature in order to decrease the analysis time. So, but usually most of the time right now, we just do analysis at room temperature. So some systems do not have the carbon, or we call it the column oven. But in some HPLC system, sometimes they will offer this column oven. So especially if you want to analyze or separate biological compounds or natural products compound, because these compounds usually they consist of very complicated mixture of samples. So in this case, we cannot use very strong eluent. We have to use a relatively weak eluent in order to increase the separation efficiency. So in other words, when we use a weak eluent, meaning that our analysis time will be very long. So in this case, in order to decrease or to make it a bit faster, we can increase a bit the separations temperature, so that with good separation as well as relatively acceptable time, then we can do our best separation conditions. Yeah. So after being separated, we need to see what is already separated. Therefore, we need a detector. Yeah. So today I will talk a bit about the detector, and then after the detector, usually the detector will be changed from analog, will be changed to digital. so that we can see the data using, usually now is Excel. So all the data, including the plate numbers, the peak height, peak area, everything will be come out in Excel file. It's very convenient now, yeah. You don't have to draw, you don't have to calculate by yourself. Or when you buy the system, usually they will offer data software, which is actually quite expensive. So sometimes when you choose the data processor, also it's very tricky, yeah? Because some famous company like Shimatsu or another company like Agilent. So when they sell their system, they also sell their software. And sometimes it's very tricky because the software used by Agilent, you cannot use with another system. Yeah? So it's very tricky. Yeah? So usually we buy our software from another small company because when the company is smaller, they are like they are more specialized only in software. They don't sell other parts like it for HPLC. So their license is free. You can connect with other detectors. And sometimes if you buy one license, you can use for 2 detectors. So in this case, we call it 2-channel. So that's why when you buy your software, it is important that you have to ask whether this software is for one single channel or 2 individual channel. Yeah? Sometimes they say you can use 2-channel, but sometimes if the 2-channel is not individual, that means you have to connect them together. You cannot separate them and just by 2 different systems. It is also meaningless. Yeah. So when you try to ask for the software, if you want to use for 2 system, 2-channel, especially when you have a lot of students, you want to use for 2 system for 2 students, then you have to ask for 2 independent channels. Yeah. Anyway, this is for data processors. So I believe, if I ask, of course, the column, the column is the heart of chromatography. But beside the column, like the palm, injector, detector, data processors. Okay, which part do you think is more important than the other parts beside the column? Yeah? It's, yeah.
Okay, come on, participants. Can you answer?
Sorry, yeah. If somebody have any answers or yeah. Yeah, the column is the heart. Yes, Putri, thank you. Yes, the detector. Yeah. So the detector will be very important, especially depending on your sample's nature. Like most of the time, we use direct detection. Yeah. So direct detection means whatever nature the sample has, we use it. So today I will talk a bit about the detector. But before that, actually each of the part is also important. Palm, of course, if your palm having, sometimes the plunger problem, then your sample, your retention time, everything will be run off. Yeah? And then, for example, if your column is too small, like if your diameter from 4.6, if you change to 2.1, but you forgot to change your injector volume, then your separation also will be very bad. Yeah. So comparing to the columns, you have to calculate the total volume of the column. So for example, if your column diameter is 4.6 mm, which is the conventional size, and the length of the length of the column usually is 25 centimeter or 30 centimeters. So in this case, the standard volume for the injector will be 10 microliter. Yeah. But if you reduce the column diameter to 2.1, from 4.6 to 2.1. That means from 4 mm to 2 mm, it's becoming half. To when the diameter becoming half, of course, the volume will become 25% less, 1/4 less. So in this case, your injector, you have to reduce the injector from 10 micro to 2 micro. Yeah. So usually we don't, most of the time they don't sell 2 micro injector. So you can use 1 micro. Sometimes you can use 5 micro, but yeah, the maximum is 5 micro. Don't use anything more than 5 micro. If not, your peak will be so broad. Yeah. So anyway, yeah, when you buy yours in the future, if you have the time and become a researcher in a lab, so usually the it's like a computer now, you know, the system, HPLC system, they will sell in a set. Yeah. So they will already give you the best set with the best combination. So you don't have to think. So it's like buying a PC. You don't have to worry about the memory. You don't have to worry about the motherboard. You don't have to worry about the graphic card or whatever, because they will come in a set. So the important things you need to look at is the detector. So sometimes the detector and the software also will determine the price of your system. So, okay. So today, like usually this is the steps. I just want to introduce how we develop a method for in HPLC. For example, like you have to have the information of the sample, and then you have to define your separation goals. So meaning that for this sample, how much accuracy or what are the information you want to get. So you have to first set your separation goals. Then after that, you have to know whether if this sample, do you need to do pretreatment or not. So if your sample is clear sample, like tap water or even like a river water. So this kind of water is a bit clear. So usually you just do pretreatment like filter. Yeah. So you just use a filter like the one I showed you last time. So you just use a filter and filter the sample, and then you can inject the sample already. Yeah. But sometimes if your sample is like vegetable, like carrot, you know. So for example, if you want to determine the pesticide in the carrot or pesticide in a vegetable. So in this case, you have to do pretreatment. You have to cut the vegetables, and then you have to homogenize the vegetable, and then you have to filter, and then you have to evaporate. So the pretreatment will take 1 day. So it takes time. And sometimes for sample containing protein, like a blood or whatever, you have to do deproteination. So this kind of procedure will have to, you have to follow the standard method sometimes if you're in the QA, you know, QA department, I mean, quality assurance. Yeah. So most of the company, like a drug company or the food company, they must have a QA department to make sure the quality of the drugs and the quality of the food it's up to the standard. Yeah. So they will have a HPLC system to do all this. Yeah. And then after that, you can see here, the third important thing we need to do is to choose the detector and the detector setting. So detector setting, the important setting is of course the wavelength. Later I will explain a bit the wavelength. So the detector will determine whether your sample, if your sample has a chromophore, it's very easy, just use UV. And then, but if your sample do not has a chromophore, then you have to see what kind of, is it ion sample or is it not ion sample? Then you can determine what kind of detector you want to use. Then after that, only we choose the column. Yeah. So see whether what column is good for this separation. Is it absorption? Is this ion exchange? You know, something like that. And then we just do like a test run, just testing and estimate the separation conditions. Yeah. So in order to know how to estimate, you need some experience. And in order how to get the experience, you need to do a lot of reading. Yeah? So by reading and by look at other separation conditions, then you can know or you can guess what is the estimated separation conditions. Then after that, you have to optimize so that we can get the best separations between the best time. We do not want to waste time, but at the same time, we want to get a good separation. Yeah? Then, of course, you will have problems like the peaks overlap, and sometimes you have tailing, sometimes you inject the peak, but there's no peak. So sometimes there will be something like this. So depending on your column or depending on your eluent, usually we can improve by changing the eluent or by changing the detector wavelength. Yeah? So after that, you can set the quantitative calibration. This is to get the determination results. Sometimes you can just enough to have the qualitative. So, but in most of the time, we have to do recovery. Yeah? So in recovery, usually we have to compare with the standard samples. So, well, these kind of steps will be like important to actually determine the, the reliability of your results. Yeah. So if you have some results and if you repeat 3 times, minimum 3 times, you have to repeat, but the results become very different when you calculate the RSD. RSD means relative standard deviations, and the RSD is more than 5%. That means it is not so good. But sometimes for some samples, as long as it is less than 20%, some people can accept it. Yeah? But usually for the good HPLC system, the RSD have to be less than 5%. And if the system is very, very good, then the retention time, the RSD for retention time should be less than 2%. Yeah. Then finally, you can introduce this method by, you can publish a paper or in some company, because to the company, sometimes the papers, they don't care, but they want a patent. So usually they will like register for the patent. So if anybody want to use their method, or if anybody they want to sell their products, so they will have, for company, they will have patent. But for university, usually, I don't know, most of the Japanese university, like, because to maintain a patent is not cheap. And, as educators, if you have a patent, not many people can buy, and that even though your system is very good, but if people want to buy and use it, it is not so common. Yeah. So if you are not worried about the money, you just publish the paper, because if you just want the paper and show that this is your originality, then everybody can use your method. Yeah. If you remember, some years ago, Professor Suzuki and Professor Miyaura, they have this Suzuki-Miyaura coupling, right? So Professor Suzuki was in Hokkaido University. Yeah? So he is very famous, and then in organic synthesis, of course. So when we have the chemical society meetings, some people ask him, yeah, if you have a patent, then your coupling reaction will sell so much money. Yeah? Then he said, I don't want to have a patent because I want everybody to use my reaction. Maybe because of that, he get the Nobel Prize, because so many people use it for so many different applications, and therefore he got the Nobel Prize. In Gifu University, we also have a famous professor in organic synthesis. Her name is Kaori Ando. She also 20 years ago, before when she was in Tokyo University, she invented the Ando reagent. So under reagent is for the synthesis of the Z selective compounds. So it's like when you do some organic synthesis, when you have the Z selectivity and the E selectivity for the chiral compounds. So if you use under reagent, according to Professor Ando's papers, 99% you can get its Z selectivity. So this is how good her reagent is. And recently, she agreed to let some company to commercialize and to sell the reagent. So all this time, she didn't have a patent, and then a company agreed to buy her reaction, and then the company talked to her. They want to use it to commercialize the products. And recently, she gave her permission to this company to sell her products. So there are some professors like that in Japan. Yeah. So later on, I will introduce one technique that we can use in HPLC. Well, yeah, later I will explain about that technique. So anyway, if you Google, at the moment, I think most of you are very good in using Google or using internet. There are so many different detectors for HPLC. Like the common one, maybe you usually see the abbreviations, short forms, UV or UVVs or PDA detectors. And then second type is reflective index detectors. So as the name implies, reflective index will use the refractive index, like it is this detector is using the differences between the angle when you change from one media to another media. So in the detector, what is important is the flow cell. Yeah? Flow cell means is the small chamber that the eluent will come and the light will pass through. That is where you get your detection. So we call it the detection window. Yeah? So the flow cell is very important. And for this reflective index, the flow cell will have two compartments. One is for the standard, one is for the sample. Yeah. So this is how that by changing the reflective index, you can measure any sample, because any sample go through two medium, any sample can have a reflective index. Then the third type is evaporative light scattering. So this is usually we use for some particles or something that can scatter the light when the light pass by the sample when there's a scattering. Yeah? And then another one, which is quite similar, is called multi-angle light scattering detectors. Then number 5, of course, this it's very expensive, but very good. One of the best detector is the mass spectrometry, spectrometer. So spectrometry is the method, yeah. Spectrometer is the detector, yeah. So when we talk about detector, we use spectrometer. So this is a mass spectrometer. And then, like the name implies, we have to ionize the samples and we have to determine the mass. Like in this case, we have to use the sample which is volatile. The sample have to be ionized. Yeah? So it is good for small molecules. Sometimes for big molecules, it is not easy to ionize and you cannot ionize, so you cannot use the mass spec. Yeah? The number 6 is conductivity. So you can see the name conductivity. We measure the conductivity between the eluent and the samples. And you can imagine it is mostly from ionic samples because ionic samples, we have a very good variety changes of conductivity. Yeah? Then fluorescence. Fluorescence is another very specific. The wavelength of fluorescence is very different from UVVs, and therefore the fluorescence is very selective. Yeah? Another one is the chemical reactions. So after passing by the separation column, by applying some chemical reaction, we call it the chemiluminescence detector. So this one is also very selective to certain compounds that have the reactions. Another one is the optical rotation. So optical rotations is like the, like the level and textural. So this is it's usually for the chiral compounds. So it is not so common right now, but it is important when we want to use for chiral compounds. And last but not least, any sample that has the electrochemical reactions. So it is a bit different from chemiluminescence, because this one you have to have the like a luminant, luminate. It's like you can see some changes in color, and this one is like the changes in the electricity. So the mechanism is a bit different, but most of this kind of detector, it's in the market. So depending on your samples, you have to choose the different detector. So anyway, I think last time when you were given the textbook from Gary Christian. So in the second part, the instrumental parts, Gary also have explained a lot of detectors in HPLC. Maybe you can read in details. So today I will introduce a bit about the first type, UV-vis PDA detectors. So, but before that, I want to give you the common abbreviations. So maybe you don't have to, you already know, yeah. Ultra UV, of course, is for ultraviolet. So vis mean visible light. So UV usually is between the wavelength is between 190 to less than 400. Yeah. So in this area, it is, we cannot see the color, anything. So in this area, it's usually UV, the ultraviolet. So visible usually is more than 400 nanometers. So usually from 400 until we do 600, but sometimes some detectors have 700. Yeah. So usually for UV, usually is 200 to 400, and then vis is from 400 to 600. The rest we do not use. Yeah. So PDA is, we call it the photodiode array. So well, photodiode, if you Google, maybe you can know, is also the type of different light. So we call it PDA. Refractive index, we call RI. And evaporative light scattering, we just call ELS. And then the multi-angle mouse mass spec, we say mass spec, and sometimes we just say, when we combine HPLC, we just say LCMS. So LCMS, it's very important right now, especially with the omics separation. So omics, it's a very complicated kind of complicated and yet very important type of knowledge. I think in the webinar, Dr. Rafi, who is the current president of the Chemical Society of Indonesia, he will talk about metabolomics. So metabolomics is the youngest in the omics family, but you can genomics, transcriptomics. So if you Google, you can have a lot of omics, yeah. So in my previous lab, when I was in Nagoya University, my supervisor, he's already retired. So Professor Haraguchi, he started, or he invented a new omics. We call it metalomics. Yeah. So metal means the metal, the metal, yeah. So metalomics means because his major is ICP, yeah. So ICP means is a kind of very famous detector to determine heavy metal ions. So Professor Haraguchi, he has published more than 500 papers before he retired. So during his retirement parties, when we try to summarize all his papers, he was having almost like 530 papers. Yeah. And I was so lucky, I was his last PhD student actually. So it was it was an honor for me to be able to join his group. So Professor Haraguchi, he's an expert in ICP. So when you talk about ICP in Japan, everybody knows about Haraguchi sensei. He is still active now, but at home. So he is staying in I don't know if you know the Kanagawa prefecture. Kanagawa prefecture, I think the famous is the Yokohama. Yeah? So Yokohama city is a famous city. So his house is there in near Tokyo. So with his wife. Anyway, this ICP is the important determination is heavy metal ions. Yeah? So he invented metallomics is because, you know, in our body, we have so many metals in our body. Yeah? For example, for a woman, you know, sometimes you need iron, right? Like anemia. Most of the women, because of our body's nature, most of the women will have anemia. Yeah. So in this case, usually you have to take a supplement like ferrum. So our hemoglobin has ferrum, and then we have so many other metals, important metals like in our body to keep our functions of our body. So Professor Haraguchi invented metallomics. So it is a form of new knowledge to determine the metal combined with different complex inside our body. So it's very difficult to do because the pretreatment is very difficult. But ICP also, it is not so cheap. So it is a very expensive matter. But we have, when in year 2007, Ghana, he, with just the year, almost the same year as his retirement, the year before his retirement ceremony, we managed to organize the first metallomic symposium in Nagoya University, in Nagoya. So there are so many professors from Harvard University, from Cambridge, they all come to attend this symposium. I think the main aim is to visit Japan, but because of this, you know, when you attend conference, beside the scientific exchange, you need also culture exchange. Yeah? So we also take our guests to visit Nagoya, to visit the Japanese shrine, and to eat some Japanese food. So I hope someday you can come to Japan and visit. In the webinar, I plan to introduce some of the international conference we have every year. I mean, before the corona, yeah. Hopefully after the corona from next year, the Chemical Society of Japan will try to organize again. So I will recommend one or two conference, which is interesting for you to come. And sometimes some people don't know, but we also have travel fund for overseas traveler. So maybe, you know, when in the future, when you become a researcher in some company, or when you become a docent in a university, you can come and attend this kind of conferences in Japan. So, but anyway, sorry, I've talked too long. So for conductivity, we usually say CD. So when you say CD detector, CD sometimes stand for cyclodextrin also, yeah. But when you say detector, CD stands for conductivity. Then fluorescence is FL. So chemiluminescence is CL. Optical rotation is OR detector, and EC detector. So, okay. Like the first type here, I told you, the UV-Vis PTA detectors. So today I will talk about this type of detectors. So if you Google on the internet, you can see different companies. They have different dimensions of the detectors. So if you try to look at their products, they all have the same color for the same company. So for this one, if you look at this color, like the black color and the gray color like this is standard color for Shimadzu. So Shimadzu is one of the most famous company, of course, with 2001, when one of the researcher, Dr. Koichi Tanaka, become the Nobel Prize laureate. And then I think he was the first Japanese, I mean, the youngest that time, the people, I mean, who received the Nobel Prize in chemistry without a PhD degree. He didn't have his PhD degree yet. He was a researcher in the company. So if you look, his story is very interesting also, yeah, because they found the method is a mass spec detector, yeah. So they have found a new detection ionized method, which is we call it the TOF, time of flight, yeah. Time of flight mean the time for the ion to fly to the detector, yeah. So it's very, yeah, the name is very funny, yeah. Time of flight. That means for them, they imagine the ions after you being ionized, you will fly from one side to one side. So under the vacuum, yeah. So under vacuum, when the ions is being ionized, the time passing through the vacuum will depend on the size of the mass. So yeah, it's one of the most expensive mass spec in the world, and they managed to do for so good in the structural determinations of protein and all the biological samples. Yeah. So I heard that time the team leader was, of course, the whole team was a Japanese people team. And then I heard that time because the team leader actually wrote a short paper in Japanese before, but Dr. Tanaka's, after that, his English is better. So that's, in the next year, I heard he wrote a full paper in English. So that was the paper that was accepted to be considered for the Nobel Prize. Yeah. So in other words, it means if you want to get Nobel Prize, you also need to study English. Yeah? So, but anyway, this is another different story. So if you look at this color, this is a very standard color for Shimadzu company. In my lab, we use this detector. This is by Jasco. Jasco, not the Eon, the shopping mall Jasco, yeah. So this Jasco is JASCO. In Japanese, it's called Nihon Bunko. So Nihon means Japan, Bunko means spectrometer. Yeah? So Jasco is they first started their business in spectrometry. So they are very strong in selling a lot of different detectors. So usually we buy this detector from them. It's cheaper compared to Shimadzu. So we buy a cheaper one. So Jasco have the blue color like this. So this is the usual one we have in our lab. Anyway, the first, this category, the easiest detections is called we call it the absorbance detectors. Yeah. So meaning that whatever we can detect and the light, like the UV, the sample will absorb something, and then that's why we call it the absorbance detectors. So the second point is they provide relatively good sensitivity for light absorbing compounds. And sometimes if you can optimize, you can get maybe picogram level detection sensitivity, which is very high, but it is not, most of the case is like 10 to the minus of 6. So you cannot get too high sensitivity sometimes. And then, but the good thing about UV, about this kind of PDA or the UV-Vis detector is it is very easy to operate and it is very stable. Yeah? So this is a PDA. This one is a UV. The same company, usually from outside, you cannot know the difference. Yeah, you have to look at the name of the detector. But when you open this window, sometimes you can see the connection part is a bit different, but usually they are almost the same. Yeah. So you have to look at the name first. So for why the company have the same type of design is because when you want to put your system, you don't want to use so much space. So usually they will have the same size so that you can accumulate, you know, like you can put them like this and then or like this, you can save the space. Yeah. So usually if like for this is the Jasco detector. If you look a bit careful here, this one small dam part, and then these are the dam. There are 4 places. It is for the 4 tools of the other detectors or the pump to go on top. Yeah. So you can usually the pump, the detector, everything will be similar size, similar design. So you can overlap them and put together so that you can save some space. So it is easier. And another point is, compared to PDA, UV-Vis is the most commonly used detector for HPLC analysis. If you look at the standard HPLC set, usually, I can say 90% they will come with a UV detector. Yeah? Because UV detector is the most easiest operating detector with, like I say, relatively good sensitivity. Yeah, not so high but not so low. It's like in the medium. Yeah. So it's enough. It is already good enough. You want to see anything. So if you optimize the condition, if you optimize your injector, you can get very good sensitivity, yeah, depending on your sample or depending on how you optimize your system. Yeah. So well, it is the same. Yeah. When you buy something, yeah, how good you can get something depends on the operator. Yeah. So if the operator is very experienced, you can have a lot of different idea to increase your sensitivity. Yeah. So in order to get this, sometimes, when they some student ask me, how do you know this one is like this? Yeah. So sometimes I just make fun. I just say, okay, I have 6 sense, but actually not 6 sense. It's by experience and it's by a lot of readings. Yeah. So I read a lot, especially when they in the beginning. But right now I'm just so busy, so I don't read so much. But usually in my lab, we have I think the research or the education system in Japan is quite different. When I was in Malaysia, it was different. After coming to Japan, we have this lab system. Yeah. So the students will stay in the lab, in the same lab, and every week we have this ZEMI. ZEMI, if you translate in English, is called seminar. Yeah? So every week we will have a seminar with all the group members. So all the group members will take turn to present something. Sometimes it's to present some progress report. Sometimes I also let them to present, to introduce some papers. Yeah. So for the student will look at from the database, one of the latest or one of the papers that they think is interesting and related to their research. They will introduce the papers, and then from that they will compare. I ask the student to compare to the papers, what is good about the paper and what is good about their research. Yeah. So in this case, we can improve the students' ability in research. Yeah. So that is why the more you read, the more experience you will have, and then it is easier for you, or it is faster for you to get the best operating conditions. Yeah. Okay. Thank you. So another thing that you need to, sorry. Okay. So during the analysis, some samples, the samples, yeah, will go through a clear colorless glass cell, which we call the flow cell. Yeah. So the flow cell is actually very important in the detector. Yeah. So, and then you have to be colorless and like totally transparent. Sometimes some people use glass, but most of the time it's like a quartz. So you have to be very clear. Yeah, of course, glass is also very clear, and you have to be robust so that you don't crack the glass. So, and so usually we don't change the flow cell so much. Yeah, but for a normal HPLC system, yeah. But for capillary system, we have to change the flow cell from time to time, and you need some technique for that. Yeah. Anyway, after when the UV light is irradiated on the flow cell, the sample absorbs a part of the UV light. that's why this kind of detector is called the absorbance detector, because the sample have to absorb a part of the UV light. And thus, the intensity of the UV light observed for the mobile phase without the sample and the eluent containing the sample will be different. Yeah. So how we measure, we just measure the difference. Yeah? So meaning that the eluent also it's have to be UV transparent. Yeah. So if your eluent is having so high UV, then when your sample come in, you cannot see, yeah? Unless you want to do indirect detections. Yeah? So sometimes, anyway, most of the time we just use direct detection. So eluent, no UV, sample got UV, and then you can see the difference. Yeah? So, but for some sample, when there's no UV, but you only have one detector, so what you do, you change your eluent. Yeah? You use the eluent with a high UV, and then when the sample without the UV, they will come up as a negative peak. Yeah? So this kind of detection method, you can use when you only have one choice. So you have only UV. So what to do? Yeah. So sometimes you have to be creative. It is important also to be creative and then try to. And I have a question from Satri. Okay, what is the function of UV in HPLC? UV is the detector, UV detector. Yeah. So if we go back to the system. If we go back to the component of this is the components of liquid chromatography. So after the column, we have a detector. So the UV detector, the detector has many types. So right now I'm explaining the UV detector. So UV is a detector to determine the sample, to detect the sample after separations. Yeah, I hope this answers your question. Anyway, I will continue with the rest. So we usually use direct detection and we measure the difference between the eluent and the sample. Okay, so okay, there's another. Okay, I know it's difficult. Okay. Functions of UV. Okay. So I hope the question is answered, right? All right. Anyway, another things when you set a UV detector, the important thing to set is the wavelength. Yeah? So you have to set the wavelength based on the sample's absorbance range. Yeah? So if you know this, for example, your sample, if your sample has like a oxyl or like hydroxyl group, benzene group, something like that. So this kind of sample will have very high UV. Yeah? So you can use a UV detector. Yeah? So chromophore, look for chromophore. Yeah? So I think this kind of information you already learn when you learn organic chemistry, maybe if you still remember your organic chemistry. So when you have a chromophore means the compounds that can absorb UV light, then you can use UV detector. If you look at all the compounds around us, more than 80% of the compounds has UV. So it is very easy to use UV detector. But the important things you need to remember to set the correct wavelength. This is because different sample will have different wavelength for absorptions for UV. So they will have a separate spectrum. So I think in the internet now, if you just Google your sample, for example, benzene, or something phenol or something chlorophenol or whatever, when you Google on the internet, you can see the spectral UV spectral on the internet. Then you can choose the maximum, the lambda max. Yeah? Then choose your lambda and then choose the wavelength. Then you can set that wavelength in the okay, thank you, Faika. I'm going to explain this later. Yeah. Okay, so choose the lambda maximum for your sample. Yeah, and then for UV, sorry. So for the standard UV detector, it allows us to choose the wavelength between 195 to 370. Yeah. But the most commonly used is 254. And then for a visible, because visible is a bit higher than the UV, and it is usually between 400 to 700 nanometer size of the wavelength. Just now, I just have questions like, is it correct to combine between UVVs and PDA for detect? Oh, yeah, you can combine, yeah, because I have a questions. Is it better to combine UVVs and PDA? Usually UVVs is one set, yeah, because most of the company, they want to sell. If you just sell UV or you just sell this, it is difficult, yeah, because we want to use both most of the time. So usually they will sell as a UV-vis detector, yeah. So they will have the wavelength between 195 to 700, yeah. So this is a very common type right now. I think like I think most of the time it's all is UV-vis, yeah. You very rare you can just have UV detector. Usually is when we say UV detector, it means UV visible detector. Yeah. So because it's very easy to add another lamp for the visible light. Yeah. So okay, for the PDA, you can combine PDA if you want, but UVVs, PDA, they are the same functions. That means it's based on the absorbance. Yeah. Okay, since I already have questions, do you know what is the main difference between UVVs and PDA? Photodiode array. Maybe it's difficult for you to know. Anyway, for the PDA, the photodiode array, the detector will absorb the whole spectrum. Yeah? But for the UVVs, there is a single wavelength. Yeah? So meaning that the dimensions of detections for UVVs is wavelength. I mean, is the absorbance and the time. Yeah? But for PDA, you also can absorb the spectrum. That means you can have the best, you can know what is the best detection wavelength based on different wavelength. Yeah? Because when you use a PDA, you can have the different wavelength. They already absorb the whole spectrum. In other words, you can save some time to determine what is the base wavelength. Yeah? But most of the time, when you look at the compounds, if you are already experienced, you know which wavelength to use. Yeah. For example, the UV detector here. When we want to use the UV detector, what UV lamp as a detector, sorry, I have a question. Yeah, is there an error in the research and it turns out to be happening to the detector? Usually, why and how it can happen? Okay. So this question from Vita, yeah, there is sometimes an error in research turn out to be the detector, especially when your eluent, when your system, if you look at your system, sometimes your eluent, your pump is running, your eluent is coming out, but there's no detector, there's no peak. Yeah. So sometimes especially when somebody share your detector, yeah. So when somebody use it for detections of, for example, ions, is some ions have UV, yeah, but the ions UV usually is lower wavelength, like 210. So when you use 210s, and sometimes when somebody else say they want to borrow your samples, and sometimes they set their sample have a color like a visible color, you know, and sometimes if they set their wavelength like for example 430, yeah, for them is okay, yeah. But then after that, when somebody return your UV detector and they just connect for you in your system, but if they didn't tell you they use it, and if they forget to change the wavelength back to your wavelength, so if the setting is 430 wavelength and then you want to use it for your own sample, then you can never see the peak. Yeah? So in this case, when sometimes my students say there is no peak, then I will ask, the first question I ask them is, your eluent, does it come out, the waste of the eluent, does it come out? Then they will say, yes, it's come out. So, okay, that means the system is okay, the pump is okay, everything is okay, it's connecting, there's no leaking. Yeah? If there's no leaking, then I will ask them, have you checked your wavelength? Then they will check the wavelength. Yeah? If this wavelength is also okay, the system is also okay, then the next thing you have to ask them, when did you make your sample? Yeah? Sometimes when the sample is so old and which is not stable, sometimes when the sample is not stable, then after some days, for example, if you make the sample on Friday, you do experiment on Friday, but you cannot get good results and you want to rest and then you go back, then Saturday, Sunday, 2 days, you live in the lab under the hot condition, like the room temperature in Indonesia is so hot, then your sample will become broken. Yeah. Then on Monday, if you use the same sample again, then you cannot get any peaks. Yeah. So there is a time usually there will be some error. Yeah. Okay, thank you. So yeah, I hope, yeah, like this, you can ask questions from time to time. I hope I can answer them. I will try my best to answer them. So now I have the most common, like here, explain about cutoff UV. Cutoff UV is, okay, I have a questions from City. Oh, so yeah, City. Yeah, cutoff UV is something that we use to increase the sensitivity of the UV. So usually we don't do so much cutoff UV, but sometimes the cell, the design of the cell, of the flow cell, it's already have some certain cutoff, because if we do not use the cutoff UV, sometimes the noise, the background noise is so bad, we cannot see the peak yourself. So usually the cutoff UV is to increase the sensitivity of your sample so that you can reduce the background noise. Yeah. I hope that answers your question. Right. Okay. Hi. So okay, like I say here, UV, the common one is 254. Yeah. So why 254? Anybody wants to know? Anybody has any idea? For those who have experience, I don't know how many of you have experience before. $254. Last time, you know, 254 now, if you ask people who have a UV detector, I don't know how many of them still know why you set 254. Yeah? But usually, most of the sample, organic sample compounds, contain benzene ring, right? Benzene. Almost all the benzene, I can say 100%, can absorb UV at 254. Yeah? But then sometimes lower wavelength, like 220 or 208, benzene also have very high absorbance. Yeah? There was one time I was wondering why this UV is so common to set 254. Yeah? And then after that, I searched the history of the detector. Then I find out the original or the first generations of the UV detector used the source of light, because you have to give the light source for the UV. At that time, they used mercury. Yeah? So mercury light, only one wavelength, which is so bright at 254. Yeah? So at the time, now because of the regulations, everybody we try to not to use mercury. Yeah? You can imagine when the inventions of mercury, it's so good, you know, in thermometer. Yeah, thermometer now we don't use. If you look at the thermometer in your lab now, I think we don't use mercury anymore, right? If you look at the color now, is it silver color like a mercury, or is it the red color? Yeah, which one? Which thermometer are you using in the lab right now? The red color, right? Type, right? I think it's the red color type of thermometer. So for mercury, we already changed to the red color. Anybody know what is the red color cause? What is the liquid used in the modern day thermometer now? Not mercury anymore, yeah? Anybody knows what we use inside now? This is general knowledge. Yeah? You have, please remember, the thermometer now we use is from alcohol. Yeah? So we it is already optimized to have a certain Celsius. We use Celsius a lot, but sometimes in America they still use Fahrenheit. Actually, Fahrenheit is the original, but in Japan we use Celsius. I think in Malaysia also we use Celsius. In Indonesia also, yeah. All right. So 254 now is because the original UV detector used the mercury lamp, and the mercury lamp, the source of light, have a very high absorbance as 254. Yeah. So, but now we don't use mercury lamp. Usually we just use the tungsten, yeah, tungsten lamp to as a source of light. But still, 254 is commonly used for organic compounds. Yeah? So it is very common. So anyway, it's so fast. 1 hour has passed. Anyway, so there are still many types of many different detectors that you can study from the textbook. Today I introduced UV is because 90% of the HPLC system has a UV. Yeah? That's why I thought it is important to know more details of UV, which you cannot get from the textbook. Yeah? Anyway, I would like to compare, there are many detectors, but I would like to compare some sensitivity of some detectors, like in this slide. So if you look at the sensitivity here, the unit I use is nanogram per milliliter. Yeah? So milliliter, you can convert to as gram. So nanogram per gram means that it is a ppb detection limit. Yeah? So when you have a ppb detection limit, if you look at here, from the universal, like the RI, refractive index, you can detect, this is a limit. Yeah? Limit means the lower, the better, right? So you can see, if I compare these 5 detectors, it has slightly different sensitivity. Yeah? So refractive index is very universal. That means you can see anything. And of course, the sensitivity is lower. And for fluorescence, its sensitivity is very high, but you can see it's selective. Yeah. So UV, why I say UV is so popular now, when we say UV, usually is UV vis. It don't come as a single UV, it doesn't come as a single vis. It's always UV vis. It's so good in selling right now. It's certain selective because you can only use it for chromophore for the original detections. And if you look at the sensitivity, it is right in the middle here. It is not so low, and it is not so, of course, it's not as high, but it is good enough. Yeah? So meaning that it's very easy to operate, it is very stable, and it is very cheap. So that's why it is so common. Yeah? Mass spec, on the other hand, is very it becoming more popular now because of the omics research in so many different kind of research for biological samples. And some textbooks say this is a universal detector. Some textbooks say this is a selective detectors. And of course, you have to ionize your samples. So if the sample is not volatile, cannot be ionized, then you cannot use it. So in other words, it is selective. Yeah. But on the other hand, as long as you use high ionization energy, anything can be ionized right now. Yeah. So if you study, if I want to give a lecture on mass spec, I will need 1 more hour. Yeah, because the selection of mass spec for the ionization method has so many different ionizations. So please read the textbook from Gary or the textbook by Scotch under the mass spec. Please read chemical ionization. Please read ESI, electron spray ionization. And at the moment, the most popular one is, we call it MS, the mass TOF. TOF means time of flight. So these three are the popular ones. So ESI, electron spray, is also popular. Anyway, you can, to have better understanding, maybe you can Google in YouTube, you can see the video. Yeah? It is more easy to understand how they have very good ionization videos. Yeah? That's why I don't introduce here, because I think you can Google YouTube, and there are so many good videos how to say, supplied by the company. Yeah? Because the company, they want to sell their detector, so they also introduce many videos in YouTube. You can learn some ionization method using the mass spec. So this is a way how we want to choose the detectors. Yeah, depends on what it's your goal for getting from the sample. Yeah, if you want very very small, very sensitive detection, then you have to choose a very detective sensitive detectors. Okay, as I say, when I don't know, maybe some of you heard when I was talking to Maura, in the second part of my lectures today, I want to introduce a technique that we call it recycle LC system. Yeah. So this recycle LC, it was used many years ago as to do preparative. Yeah. Preparative means to get to separate some compounds when you have after your synthesis. Yeah. So it is usually was used in some organic synthesis, but we optimize this system to use for analysis of some samples. Yeah. Okay, when you hear the words recycle, yeah, what is in your mind? Yeah, what do we recycle? Yeah, does it mean we recycle the column after it's being used? We reuse the column. Yeah. Okay, I will do some introductions. When you have a very difficult separations, there are only two ways. Usually, you know, how do you want to improve your separations? The easiest is to change the column. Yeah. But if you cannot change the column, then you have to optimize the mobile phase conditions. Yeah. So this is the normal way when you want to improve the separations. So another one is, you can, if you have another column which is free, I mean, which is you are not used, you can connect two columns, because when your columns become longer, you can have a better separation. Yeah. But in this case, like I said before, when the column is too long, the pressure of your system is very high, and sometimes your injector or your detector will become leaking. So in other words, you have to check the inlet pressure of the system so that you cannot have too high pressure, and at the same time, you can have some good separations. Another thing is what we say here is recycle. We recycle the sample through the column. Yeah? So if you imagine after one-time separation, when there's no separations, we recycle and give them back inside the injector, inside the column and separate again. This is what we call the recycle LC. So recycle chromatography is an approach where the sample is being recycled through the columns, or one column is also okay, but if you can have two columns, it's even better, and thus producing the same separation effect as when a relative long column is being used. Yeah. So the advantage of this recycled chromatography is it allows the separations of compounds with very near retention time. Yeah? And you don't have to increase the inlet pressure. If you just recycle one column, just one column and recycle, the inlet pressure will not be increased because it's the same column, it's the same system, you just change the flow direction, yeah. So the same inlet pressure. And then you can solve the problem of having difficult in making long columns, yeah? Because sometimes it is so difficult to pack long columns. Yeah? So that is why these are the three important advantages when you use recycled chromatography. But on the other hand, once the analytes are being separated, it will be difficult to adjust the timing, how to recycle, yeah, because there might be a possibility they will become mixed again, yeah, during the recycle line. Yeah? So meaning that the point is the peak can only be recycled until they begin to overlap. Yeah? So later I will show you some of the results, and then maybe you can imagine how we recycle this in our, it's a very old approach. And then usually there are two ways. One we say, we call it direct pumping. Yeah? Direct pumping means that the same thing, we use the valve and then the pump will go to the injector, go to the column and detector, and then we use a valve after the detector. Sorry? Oh, sorry. This.
Yeah, it's okay, Prof.
Okay.
I have mute her.
Okay. Sorry. So direct pumping system means after the detector, we put a valve here. So whatever here, after the detector, we will pump back to the system. And then another type we call the alternate pumping. So alternate pumping means that after the detector, we direct it to another column. We don't go through the pump. Yeah? So this is because alternate pumping is better, because if the depth volume of the pump is so high, then during the recycle, the sample will be brought again and they will become mixed again. So we can reduce the possibility of the mixing. Yeah? But another thing is, if you want to add another column, maybe it's so expensive, yeah. And then maybe if you have two columns connected to the detector, but your detector flow cell maybe will experience high pressure. Sometimes when the pressure is too high, maybe your cell will become broken sometimes, yeah. So another thing is how we want to control the switching, yeah? Because if the valve here, you have to have the good timing to know when the column, when the sample passes the column, then how you want to do the switching. So if you switch wrongly, maybe the sample will go to the waste. Yeah? So you cannot recycle you cannot recycle your sample. So anyway, at the time, our aim is to develop alternate pumping using capillary system. So, but we use a very low depth volume valve. So this is a system we used before. We use a switching valve by this Upchurch Scientific, which is, I think we could find is the cheapest valve that time. Well, if you look at eBay or auction, it's very cheap now. They are selling the used one is very cheap now. And but I think the postage to post from US to Indonesia is more expensive than the valve there. I remember to buy a new one through a Japan company, it costs about if US dollar, it costs about 1,500 US dollar, which is so expensive. Yeah. So after some times, my valve was broken. So I want to see whether if I can buy some parts. Then when I checked the eBay, the same valve was selling at eBay with only $20. Yeah. I was like, oh, $20. So I just click buy, and then I get I bought, at the time there was another buyer. So I bought the valve for $30. Yeah. But the postage from US to Japan was $70. So I pay almost $100 for a valve that I buy for $30. So the postage was more expensive. So okay, anyway, so we connect two short column, 10 centimeter column, ODS column to the valve, and then it's very easy to connect because this valve is we used the fused silica, and the column is only 10 centimeters. So we used UV detector, and then we use a data processor by Shimatsu. So, and the result, so this is, we use it to separate benzene and D6 benzene. Yeah? So actually this is a very difficult separation, yeah, because the difference of the benzene and the D6 benzene is only 6 different protons. So the number is just 6 numbers different. So you can see it after the first cycle, after the first column, it's like this. Then it's becoming like this, like this. So after 1, 2, 3, 4, 5, 6 cycles, then we can see slightly separation here. And 7, 8, 9, 10. Then after 13 cycles, then we see the D6 benzene and the usual benzene was separated. Yeah. But if you look at the time here, this is 120 minutes. Yeah. That means we recycle the system for more than 2 hours. Yeah. So another thing you have to see is this valve, it's actually is a manual valve. Yeah. So meaning that at the time I was a PhD student. So every 10 minutes, I have to see the detector. So when I see the peak, I have to switch. Then after 10 minutes, when I see the peak, I have to switch. So every 10 minutes, I have to remember to switch the valve so that I can recycle my system and then my sample, and I can get the peaks like this. Yeah. It was very fun waiting, but sometimes if my friend talk to me and I forget to switch, then my sample will go somewhere else. So it was very interesting when I set this system. So sometimes, when right now, so many people, they don't want to do PhD degree, but sometimes, when you can have a chance to do PhD degree, you can have free thinking to do some research. So sometimes it is also good to take some rest. I don't know, if you have, of course, some financial support, it is good to take a PhD degree and to explore some research area which you think might be able to use in the future. Yeah. Okay. Anyway, this is the first trial. I just used an ODS column, 10 centimeter, 0.32 mm. It is a capillary system, and 2 capillary system with so short, and then it was so easy to set up the system. Yeah. And then I modified the system with a monolith column. Yeah. So our group was among the earlier group in Japan to use monolith column in separations. And for me, if you can read my papers in 2004, I think I was the first person to use monolith column for pretreatment, for enrichment system. Well, at the time, it was quite popular, yeah. So, and I have many people cite my papers for their detections. Okay. Prof, one can also do PhD on, yeah, you can, yeah, on the scholarship, yeah. Try to apply for the Japan government scholarship. Sorry, I have a question about scholarship. If you want to come to Japan, or I think DICTY offers some scholarship, and the application is in March. Closing date is in May, Ghana. So you can try to look for DICTY site, LDPD, is it LPDD? Yeah, LDPD Ghana. It's very popular scholarship by DICTY, or sometimes they call it DICTYs. I'm not sure. You can ask Moral maybe, or you can, yes. And then another thing is, if you want to come to Japan, MEC scholarship. MEC stand for the Ministry of Culture, Education, Culture, Sports. So it is the, in Indonesia is the Ministry of Education. Yeah. So, but in Japan, it's including the sports and culture. Yeah. So we call MEC. So MEC scholarship, it's offered to the Japan embassy in all of the country, including Indonesia. So usually MEC scholarship will open for application in spring. Spring means from end of March, April. Yeah. So I think the deadline, depending on the embassy, yeah, please check the Japan embassy in your country. Of course, it's very, very competitive because you have to, so many people in your country want to apply for this MEC scholarship. But every year, MEC will sponsor some students. Yeah. And in Gifu University, we have this MEC scholarship recommendation. So we call it university recommendations. So every year, our university will choose some students based on the number of applications. And I was so lucky, last year, I applied for one candidate from Indonesia. Yeah, she was introduced by my ex-student. So she is a graduate from Andalas University, and then she was teaching in Jambi. So last year, during Corona, and then she told, actually 2 years before, she already told me she want to continue PhD in my lab. But at that time, because the scholarship I can offer was not so enough for her, because she's married and she has some kids. And then I asked her, let's try the MEC scholarship. So at that time, she was busy and I was busy. We couldn't apply because I have another student from Egypt, and my Egypt student got the MEC scholarship. And last year, when I applied for her, I told her, I don't know your chance because I already have one student under MEC. Maybe our chance will be low because the university, maybe they will not choose the same supervisor. Yeah? But I was so lucky and she got selected by the university, and now she's coming to Japan. And now she's coming to Japan next
Tadi
week.
nyari link, muara sok dilapoe. Ibu nyari di laptop.
Anyway, so I think maybe because I have experience to write the MEC recommendation, and of course there are so many documents. It's very difficult to, it's not so easy compared to other scholarships, but if you know the amount of MEC scholarship is very high and you can have a very good life in Japan. I mean, you don't have to do part-time job, you know, so you can have a very relaxed mind to do your research. Yeah? So at the moment, if this student join my lab, I will have 3 MEC students in my lab. Yeah? So that's why I'm so lucky to have many hardworking students working in my lab. Anyway, yeah, you can Google some of the homepage for scholarship information. Yeah? Try to Google a page called JASO. Yeah? I'm JASO. JASO stands from the Japan Association for Student Support. Yeah? So if you Google JASO, JASO has a lot of information for scholarship before coming to Japan, including the scholarship offered by the private foundations. Yeah? Many private foundations like Ajinomoto, Sato Foundations, Iwatani Foundations, they offer a scholarship better than Max. So, but one thing about Max is if you get a Max scholarship, your tuition fee, everything is also free. But if you get other scholarship, you have to ask the scholarship, you have to use part of the scholarship to pay your tuition fees. That is why if you get other scholarship, normally they offer higher than Max because it's including your tuition fees. Anyway, if you are interested to come to Japan, please Google JASO. So it has a lot of information. Okay. Okay. Yeah, please try. Satria. And good afternoon. I am SDF from chemistry again. Why during the chromatography process there should be no air bubble in the and how to choose the mobile phase of the fluorescent, how to choose the mobile phase on the fluorescent detector because it's very sensitive and fluorescent, so on. Do you have a vacancy in your lab for question? So we can try to apply but I already have another candidate waiting to apply for the next recommendation. I don't know, for those who are interested to continue PhD in my lab, please send me your CV. I will consider after reading your CV. Thank you. When we use C18 for detect sample with characteristic oily and little fatty inside the is it correct? So when you have oily and little fatty inside the compounds, you have to filter the sample before you put in the C18. Yeah. If you want to separate some compounds using C18, it is okay. Yeah. But if your sample is too oily, can you dissolve in some organic solvent like methanol? You can, if your eluent, you can use like 70% acetonitrile or whatever, then you can use. Yeah. But usually when it's too oily, you have to use a good solvent so that it will be totally dissolved in your solvent. Yeah. For master, it's difficult. Yeah. Anyway, so for we don't have vacancy for master. Yeah, because usually for master we just choose from the entrance exam. It's a bit more complicated to do masters, and then for Max scholarship, comparing to master candidates, the PhD candidates will have higher possibility. So if you want to continue master and apply for university recommendation under Max, the possibility is almost zero. Yeah. And I already have 2 candidates who wants to do PhD. So I will give priority to PhD candidates. Yeah. I'm so sorry. Maybe you can do your master somewhere first and then come to Japan for PhD, maybe. But I think LDPD they offer very good scholarship by the LDPD scholarship to study abroad and also to study in local university in Indonesia. The important thing is you have to have very good TOEFL score. Yeah, if you want to apply for your local scholarship and if you need a recommendation, I can write recommendation. Yeah. Okay, another question is about choosing about the air bubbles. Yeah, it is important. You have to, because the air bubbles, if you have air bubbles in the line of your eluent line, when the air bubbles go through the detector, it will become very bad. Yeah, the noise will become so bad. So you have to avoid the air bubble. Yeah, and the air will also have some detection and it is very, very bad. So usually you have to purge your line. Like if you look at your palm, there is a setting called purge. Yeah, Purge. Yeah. So once you purge your palm, the palm will automatically use very, very high flow rate to clean the bubble in the palm. Yeah. But just remember, before you do the purge, please make sure you have enough eluent in the container, yeah, because when at the purge setting, the flow rate is very high. So if you didn't have enough eluent, then when the eluent finish, the pump will have more bubble inside the system and it will become so bad. Yeah. So sometimes when you forget to add your eluent, that is when the filter contact with air, it will suck some air, and that is where you have the air bubbles. Yeah. So usually, if your eluent is a lot of water, like aqueous solution for your eluent, you need to degas your eluent, yeah, to avoid the bubbles. Yeah. So how to degas a sample, the eluent is very easy. You just put it inside the ultrasonic bath. Yeah. So just put it in the ultrasonic and just turn the ultrasonic for 5 minutes, and then the bubbles will be gone for 5 minutes. Yeah. Then you can use the eluent for after degassing your eluent. Yeah. And then about the fluorescence, yes, I think if you use the HPLC grade acetonitrile, you can use it for fluorescence. Yeah. That's why for HPLC, when you choose the eluent, you have to buy HPLC grade so that you can avoid the background, especially for fluorescence detector, something so sensitive like fluorescence. Yeah. Even for UV, yeah, sometimes if your separations requires very high sensitivity, and if you use the usual methanol or if you use the usual acetonitrile, which is cheaper, quite cheaper, then your background noise sometimes is not so good. Yeah, that's why you have to use HPLC grade eluent. It is expensive, but yeah, that's why it's better to use capillary system so that you can reduce the use of eluent. Yeah. Okay, I hope that is all from the question. C18. Lithophatic. Yeah, so when it's a lithophatic, then you have to choose the solvent, like I said just now. Yeah. I mean, you can still use C18, yeah. But you have to use a very good solvent so that you can, when the sample separate through the C18, the solvent or the eluent will clean your column at the same time. Yeah, yeah, BSP and molecular. Okay, so much resistant. I need 10.
Okay, I'm sorry, Prof. Because in 2:40 we have another visiting lecture.
Okay,
you can first finish your slide first, maybe.
Okay.
Yeah.
Right. So this is another for the monolithics. So we changed just now I used the PET column. Then after that we changed the monolithic column. So the monolithic column is more easier to connect because there is no depth volume here. And then when we do the same separations here, you can see we already increased the separation efficiency. Yeah? From beginning, it was not so separated, but after we changed the monolith column with also capillary, so you can see after, the important thing is when we used one cycle, it's this is the plate number, yeah, it's 29,000 plate. After 2 cycle, it's almost double, and after 3 cycle, it is almost 3 times, triple, 4 times, 5 times. So meaning that we can maintain the separation efficiency of each column at each recycle system. Yeah. So, and we also optimized and we separate even D6, D3, and benzene. Yeah. So for those who wants to, since I have only 5 minutes, for those who wants to read more details, I will introduce, this is an open access. It's very old, in 2004. So last time I have a company who asked me if I have a patent. I said, no, I don't have a patent. Please use my system. Yeah. So there was one company, they are already selling recycle system in Japan right now. Of course, they have their own patent, but I think my papers was in 2000. They refer to my paper after this, and they make the product. Yeah. And yeah, you can get my email from Mora later, or you can send your CV to Mora first. Maybe Mora can do some selection. But anyway, it's just if you have I think UPI will have some scholarship information. Yeah, maybe you can contact Mora or maybe the head of department for scholarship information. Yeah. Anyway, so you can Google separation science, and you can, if you want to read more about this recycle system. Yeah. Okay, that's all for today. Thank you. And sorry for taking so much time.
Okay, because this Zoom is also used for another lecture. So,
yeah, I'm so sorry. Yeah.
Okay, so thank you so much, Prof. Lim. Before we close this, I want to give all participants maybe some announcement. Yeah?
Yes.
Let me
share
screen first. Okay. I don't know. There's some trouble. Yeah. So, okay.
Hi.
Thank you so much for Professor Lim for kind explanation to participants. Yeah, and also I get something new, new knowledge about recycle LC, and so interesting. Once again, thank you so much, Prof. Lim, and also thank you for all participants here for your active participation during this lecture. And again, I want to inform you, all participants here, that the next week meeting, will not have held as usual on Tuesday, but replace to Thursday at 2nd December in 9 AM. Yeah, once again, Thursday, 2nd December at 9 AM Indonesian time, because Professor Lim will have another agenda in Tuesday, right? Yeah. So I will remind you again through Google Calendar. So you can check it via email. And also I want to inform you about the webinar which will be held on December 14. This webinar is closing lecture delivered by Professor Lim and the end of our lecture visiting lecture program. So don't forget to register us via link that I will send in the poster. So once again, thank you so much for all participants and also Prof. Lim. I will post this and see you next week. Bye-bye.
Bye-bye.
Thank you, Prof. Lim.
Bye-bye.
Thank you.
Yeah.
Thank you, Prof.